Hello everyone, and welcome to a new episode of the Virtual Lab series of video blog presentations on various diverse scientific computing topics. As you can see here, the topic of today's presentation is on how first principles simulations in computational materials science can assist in the investigation and analysis of the mechanical response properties of polymeric materials. So, let us begin our main scientific presentation of today. The mechanical response properties of materials, including therefore those of polymers, encompass a wide variety of very important physical behaviors exhibited under the effect of external stress loads, for example how much the material under consideration can be stretched or bent. The regime of linear elasticity is arguably the most significant of these mechanical properties, since it describes the initial response of the sample to relatively small stresses and resulting strains, whereby the sample is then able to fully recover its original size and shape upon the release of the external loading force. In general, the mechanical properties of polymers can be characterized in very much the same way as any other material, in particular through the moduli of elasticity and various other classes of strength measurements. We provide in what follows a general summary of the most important mechanical and elastic properties of polymeric materials. Firstly, the strength of a material represents the stress force necessary to fracture the material sample under consideration, whenever the applied force is stronger than a simple linear elastic deformation. Some of the most relevant types of strength quantities involved in typical materials characterization measurements comprise the tensile strength, corresponding to stretching of the polymer, compressional strength, compressing the polymer, flexural strength, bending of the polymer, torsional strength, twisting of the polymer, and impact strength, e.g. under the effects of direct hammering. Secondly, the percent elongation to break, or ultimate elongation, indicates the maximum strain that the polymer sample can attain before it ultimately fractures at the above-mentioned strength point. This quantity is therefore measured in terms of percentage change in the length of the material. Thirdly, the Young's modulus of a material is the ratio of stress to the strain in the linearly elastic response region of the material, thus effectively providing a measure of its overall mechanical and structural stiffness. Some physical factors which affect the strength and overall mechanical properties of semicrystalline polymers include the following considerations. The tensile strength of the polymer rises with increase in molecular weight. This correlation can be understood through the following reasoning. At low values of the molecular weight, the polymer chains are loosely tied together by weak intermolecular van der Waals interactions, thus resulting in low strength, whereas for the case of polymers with large molecular weights, the chains become bulky and consequently entangled together, producing high strength values for the polymer. Furthermore, the presence of a cross-linked morphology within the polymer structure inhibits the relative motion of the chains, and this results in a strengthening of the polymer. Finally, the strength of the polymer also increases with its degree of crystallinity, since crystalline phases are typically characterized by stronger intermolecular interactions. The overall mechanical characteristics of most polymer materials are embodied in the standard stress-strain curve, the simplest way to visualize the response of a general material under the effects of stress-induced mechanical deformation and loading. Such mechanical response properties are in general sensitive towards numerous external factors, such as the rate of deformation, the so-called strain rate, the temperature of the sample, and even on the presence of additional chemical products affecting the environment, such as water or organic solvents. The mechanical behavior of different classes of polymers is demonstrated in the image shown under the present slide, in the form of distinct stress-strain curves. It can be seen that there are essentially three different such classes of stress-strain behavior within the world of polymers. We therefore deduce that rigid materials such as brittle polymers have high Young's modulus, but at the same time will undergo fracture when subject to stress and associated elastic compression much earlier, in terms of total elongation strain, than the other classes of polymer materials, as denoted by the end of their corresponding stress-strain curves. At the other extreme, we find the mechanical behavior of a highly elastic and rubbery class of polymers known as elastomers, that have both low values of the Young's modulus and are capable of enduring large amounts of recoverable stretching, before ultimately breaking. For the intermediate case of ductile, plastic, polymers shown here, the distinction between elastic deformation, i.e. the initial linear part of the curve, and the plastic flow which follows, is particularly striking. The stress point separating these two behavioral regimes is known as the yield strength or elastic limit sigma y of the material. As mentioned previously, as the external stress load and associated sample strain are progressively increased even further, any material will ultimately reach also its tensile strength, Ts, at which point the total fracturing and breaking of the material occurs, and thus it no longer makes sense to continue plotting its stress-strain curve. The position of these two limiting behaviors are depicted in the image portrayed in the present slide. Moreover, it is worth mentioning that all the mechanical response properties presented so far can be significantly impacted by changes in the temperature of the polymer sample. Some examples of such thermal effects on a certain fixed polymer composition are portrayed in the image shown here, demonstrating how higher temperatures imply reduced rigidity and increased rubber-like ductile behavior. In the specific context of the mechanical properties of polymers, it is important to also discuss the issue of viscoelasticity. Under the regime of pure elasticity, the deformational strain appears immediately within the material upon application of an external stress load, and this strain only vanishes when the stress is completely released, at which point the sample will fully recover its original shape. Whenever viscous deformation occurs, on the other hand, the material does not get strained instantaneously, but rather in a time-dependent fashion. Furthermore, some of this strain deformation will be permanent and irreversible, in the sense that the material will never fully recover its initial dimensions. Typically, polymers exhibit a combination of both behaviors, in relation to their temperatures and strain rate, with elastic response dominating at low temperatures and high strain rates, and vice versa for viscous behavior. Polymeric materials are employed in a very broad array of industrial applications, ranging from construction materials to microelectronic devices. In fact, the end-use applications of polymers can be considered by itself as a classification method, consisting for example in plastics, elastomers, rubbers, fibers, coatings, adhesives, foams, films, etc. Some examples of fields of industrial application for some common categories of plastic polymers are listed in the table shown under the present slide, for illustrative purposes. A good example of a polymer material with remarkable mechanical properties is ultra-high molecular weight polyethylene, UHMWPE. This polymer consists in linear polyethylene, synthesized in a form that has a particularly large molecular weight. This specific property yields a very tough and resistant material, with the highest impact strength of any thermoplastic being currently manufactured. On the downside, this polymeric material suffers from having an unusually low melting temperature. As a result, its mechanical performance and overall strength are severely weakened at high temperatures. This exceptional set of mechanical properties implies that UHMWPE has progressively found a broad range of industrial and commercial applications, including in biomedical prostheses and implants, bulletproof vests and other forms of ballistic protection, and for the support of marine structures. The field of discovery and design of new polymer compositions with enhanced elastic and physical properties continues to this day to be an active area of research and development, particularly as a result of the sheer number of materials' compositional and structural possibilities left to discover within the realm of organic chemistry. The use of first principles simulation and machine learning techniques has often played a crucial role in facilitating such novel discoveries. Classical molecular dynamics, MD, simulations in particular lend themselves very well for computing the equilibrium molecular structure of organic materials, as well as the mechanical behavior of such molecular systems under the effects of applied stress loadings. Both polymers and polymer-based nanocomposites have been subjected to extensive investigations through such MD techniques. In the context of this short introduction, it suffices to know that classical MD codes such as LAMPS and GROMACS have in the past proven to be effective in determining both the molecular structures and the physical-chemical properties of polymer-based materials, depending of course on an appropriate and careful choice for the interatomic potential, or force field, governing the conduct of atomic motion and interactions during MD simulations and structural relaxation calculations. Several such potentials dedicated to organic materials are available for use today, both for modeling direct covalent bonding between atoms as well as the intermolecular interactions, for example van der Waals forces. This brings us to the conclusion of our presentation. Many thanks for your attention. This presentation was provided in partnership with Virtual Lab, the company behind the development of the Materials Square online platform, for executing atomistic materials and chemical computations directly on the cloud. We therefore recommend to please give a try to the Materials Square simulation platform by visiting its corresponding website at www.materialsquare.com, or more shortly matsq.com, as noted in the present slide, or alternatively also in the video description below. Furthermore, please do not hesitate to contact us by email, as also shown here on this slide, in case you would like to obtain further information on the various R&D services and solutions for materials and molecular modeling applications that we can provide at Virtual Lab. Many thanks again for your interest and your consideration.